Okay, good morning guys. Today we're going to be going over lesson 20. That's simplification of radicals and then lines parallel to a given line. And also lesson 21, which is scientific notation and two statements of equality. Sometimes, depending on the weeks and the lessons that we have, we put two lessons together. And this is one of those days, and so we'll hit it and hopefully in a good time, but explain and hopefully we can grasp both lessons. I believe we can. All right, so first off, we're going to start with lesson 20, simplification of radicals. And then we'll get to lines parallel to a given line here in just a moment. But in simplification of radicals, we remember what a radical is. Of course, it's the square root sign. And all that means is that a number had a base, or a number times a number that equaled this number. And we're wanting to get back to that base. For instance, and I'll just use this area right here and we'll erase it. If I had the number 9 and I wanted to square root that number, I would say, well, the square root of that is 3, because 3 times 3 equals that 9. And so we understand again what a square root is. It's whatever we took the square of to get that particular number. But there's some things about square roots that we need to remember, some properties. Products of square roots especially, that we're going to talk about today. And that is the square root of m times the square root of n equals the square root of mn. Notice that they have separate radicals here, their own, and then here they're under the same radical. And so the same would work with numbers as well. If I had the square root of, the square root of 3 times the square root of 2, I could say that's going to equal the square root of 6. And so those two squares, although they have their own, they're being multiplied, they're going to equal whatever's inside the radicals and then multiplied. Just kind of a rule of thumb, when we're multiplying with radicals, we can multiply, if they're being multiplied, as we'll see in 20.2, you multiply whatever's on the outside of the radicals, you can multiply those. And whatever's on the inside of the radicals, with different ones, as long as they're being multiplied, you can multiply those. But for right now, we're going to work on 20.1, and that is a simple subtraction problem. The real problem comes when we have 3, the square root of 50, and minus 5, the square root of 200, because within that number 50 and within that number 200, there are perfect squares. And so what that means is we have to pull a perfect square out. Remember how we just had the 9 over here equals 3? That's a perfect square. And so we can square root that 9 and get a number. Well, these may not be perfect squares of the whole number themselves, but inside those are some perfect squares. And so what do I mean by that? Well, let's do... what we're going to do really is break these down to a product of primes. And hopefully you remember breaking things down to a product of primes. Some people like to use the tree method here, and we would divide this by 2, and that would give us 25. Divide this by 5, it would give us 5. If you like to work this way to find your primes, that's okay, work that way. My personal favorite is to use what we call upside down division. I see 200, an even number, I'm automatically going to 2. It gives me 100. Divide that by 2, it gives me 50. Divide that by 2, it gives me 25. Divide that by 5, it gives me 5. And so either way will work. So my primes of 50 are 2 times 5 times 5 minus 5, and that's square root of 200. Those primes of 200 are 2 times 2 times 2 times 5 times 5. And there's a little saying that I've taught my kids in classes, and I'm sure maybe most algebra teachers have, when you're talking about radicals, 2n, I'm going to circle the 2 5s in the first one, 2n make 1 out. Same way it goes over here. I have 2 2s here, 2n make 1 out. I got 2 5s, 2n make 1 out. Now what does that mean? Whenever I pull the 2, if there's 2 5s in here, inside the radical, I need to pull it out to make 1 5. So in other words, this 3 gets multiplied by the 1 5 that I pulled out. So I have 15, and then inside my radical, all I have left now is the 2. Same way it goes with this one. Minus, well, I have a 5, and I have two 2s, so I'm pulling it out. It's going to be multiplied by 2. It gives me 10. And I have two 5s, multiply that out, and it gives me a 5. So 10 times 5 is 50. So minus 50, the square root of whatever I have left, is 2. So now I have 15, the square root of 2, minus 50, the square root of 2. And these are now what we would consider like terms. Kind of like having different variables. We couldn't say 2a minus 3b and get a one-term answer. We can't do that because they're not like terms. These are like terms because I have square root of 2, square root of 2. So we can actually subtract those. So 15, and all we do is subtract the coefficients, the major coefficients here. 15 minus 50 equals negative 35 and the square root of 2. And this is our answer. I'm going to go ahead and erase this so I don't forget to when I get over there. All right, we're going to look down at 20.2, a little different here now, and that's because we're not doing a subtraction problem, we're doing a multiplication problem. All right, so here's the way we're going to do it, the way I like to do it. And I'll kind of show you, some people like to do it a different way, but I'm going to, I think, show you the easiest way, and then you can decide from there if you want to do it a different way. But if they're all being multiplied, you see the little dots here being multiplied, what I'm going to start with is I'm going to multiply our major numbers here, our coefficients outside the fractions. So 3 times 4 is the fractions outside the radicals. 3 times 4 is 12. 12 times 2 is 24. So I have 24, and then I'm going to put a big long radical, and that 24 is going to be 2, and then a 3. Notice I skipped the 12 because that 12 has to be broken down to a product of primes. So 12, I'm going to divide by 2 up here, give me 6, divide by 2, and give me 3. So that's my product of primes for 12. So I have times 3 times 2 times 2. Okay, so remember our rule for radicals. 2 in, make 1 out. So I have 2 3s here. That's going to come over here. So this 24 has got to be multiplied by 3. And I have 2 2s here. And that's got to come out. So that's going to be multiplied by 2. Okay, let's see if we can figure this out. 24, I put a 3 there. 24 times 3 is 72. All right, so 24 times 3 is 72. 72 times 2 is 144. All right, so we end up with 144. And the square root of what do we have left in there? Just that 2. So 144 square root of 2. Some people like to go ahead and multiply 2 times 12 is 24. 24 times 3 is 72. And then get the 24 square root of 72 and then break that down. That just seems like an unnecessary step to me. If that way works best for you, that's okay. You can do that. Okay, 20.3. 20.3, we're looking at pretty much the same thing as we did right here, except for now we have distributive property. We remember our distributive property. We used it major with 2 binomials and called it the FOIL method. But in this case, there's only one term outside the parentheses, and so this one term gets multiplied by both terms inside the parentheses. So let's go ahead and do that. Remember, when we multiply, we can only multiply the outside together and then the insides together. Okay, so first term, 4 times 2 is we get 8. And then, oh, look at there, a 3 times a 3. Well, we know that 2 didn't make 1 out, but we'll come back to that in just a moment. Then we have a subtraction sign, or minus. 4 times, well, there's no coefficient there, so we understand it to be 1. So 4 times 1 is 1. Then inside our radical is 3 and 6. Okay, so let's do some breaking down here real quick. 4, then we have 3. So we just did this. Well, the problem is that 6 needs to be broken down to a product of primes. So it's not a prime number. And so that's going to be 3 and 2. Notice I wrote it backwards. Instead of saying 2 and 3, I put 3 and 2, just so I can get these 2 3s together so we can see it a little more easily. Then I still have the 8, 3 and 3. Okay, so now let's go back to our rule. 2 inside the radical makes 1 out. Pull these 2 out, put it right here. That 8 gets multiplied by 3. Okay, cross those out. Right here, 2 in, make 1 out. So that 4 gets multiplied by 3. 8 times 3 is 24, minus 4 times 3 is 12, and the square root of 2. Now, can we go any further than this? Well, the answer is no, we can't go any further than that because these are not like terms. This has a square root of 2, this does not have a square root of 2. And so we can't go any further than 24 minus 12 square root of 2. Okay, we're going to jump to the second subject of lesson 20, and that's lines parallel to a given line. Lines parallel to a given line. Okay, real quick, we remember our basic formula for a line. Y equals mx plus b. Hopefully you can see that. If not, you can just hear me telling you y equals mx plus b. 2y minus x equals 2 is not in that formula. I should go ahead and read that problem to you before we get there. It says find the equation of a line that is parallel to a line 2y minus x equals 2 and passes through this point. Now let's get the idea of a parallel line first. So if we had a Cartesian plane here, and we had a line on that plane, and then we had another line here. This line is parallel to this line. That means, although they may not look it, they're never going to cross ever. It doesn't matter how far up that way they go, how far down this way they go, they're never going to cross. And the neat thing about parallel lines is it doesn't matter whether they're going up, sloped up, straight up and down, straight sideways, or sloped down. If they're parallel, they have the same slope. That means this right here, the m, it's going to be the same. It'll be the same number and the same sign if they're parallel. And so we'll see how to find the equation of a parallel line if we're given the equation of one line and then a point that the parallel line passes through. So let's see. Okay, so we need to get this to the y equals mx plus b form. Well, that's going to be no problem. So we have 2y equals, we're just going to take this over here, change sides, change signs, x plus 2. Now the problem is we have a 2y, we can't have that. So we're going to go ahead and divide by 2 every term. So now I'll put it back over here. So now we have y equals 1/2 x plus 1. Okay, so y equals 1/2 x plus 1. What do we do now? Well, we're going to take our points that, now this is the slope, by the way, I'll use right here. This slope here goes in such a manner, so 1, 1, 2, so just like this. That's a sorry line. I'm thicken it up a little bit so it doesn't look so bad. That's what this line looks like. Okay, that's how it's running. As a matter of fact, it's kind of the same line that they give you in the example above it, but it just goes through a different point. So let's see if we can find out something now. Now, to use this equation, we need it to go ahead and say y equals 1/2 x plus b. Now I know, see, 1 is our b is our y-intercept. 1 is our b for this line. We need to find the b for this line. Okay, I know that's technically not a line, it's a set of points that this line passes through, but we have to have that. So how do we do it now? We're going to plug these points into this equation. So -1, because this is y, equals 1/2 times 3 plus b. Okay, so -1 equals 3 over 2 plus b. Okay, so let's go ahead and take this 3 over 2 over here, change sides, change signs. I have to make this a fraction, so it's going to be -2 over 2 minus 3 over 2 equals b. So -2 over 2 minus 3 over 2 equals b. So b is going to equal -5 over 2. And what's -5 over 2? Well, that's going to be a -2 1/2. Okay, so what does that tell us? It tells us that the b, the y-intercept, is -2 1/2. That means our line is y equals 1/2 5x minus 2 1/2, or you can say minus 5 over 2. That would be the same thing. You say, well, how does that work? Are they really parallel? Sure they are. If this pass-through line, point line 1, this would be 1, 2, maybe 2 1/2 right there. And it's still going up 1 over 2. So 1, 1, 2. So that line would still run like this. And you can see that those two lines are parallel because they have the same slope. They just cross the y-axis at a different point. And that's the thing with parallel lines. Same slope, they just cross the axis at a different point. All right, so that's a pretty simple concept. We're going to jump over to lesson 21. 21 deals with scientific notation. I know for some people scientific notation can be a little scary, maybe a little difficult to understand, but we'll try to make it as easy to understand as possible. Let's take the number, for instance, 412.036 right here. And then it says times 10 to the second power. Okay, so don't get confused, or don't let yourself get confused with the 10 to the second power to the fourth power. 10 to the second power is simply just 100 because it's 10 times 10. But why do we have the 10 to the second power, 10 to the fourth power, and even down here 10 to the negative 2 or 10 to the negative fourth power? Well, it's because in why they call it scientific notation. In science, a lot of times we deal with things that are extremely big or extremely small. A lot of times if we're in, say, chemistry and we're talking about atoms, and then maybe we're talking about grams and talking about moles of a number or a particular atom or a particular molecule, those numbers, well, those things are so minute that the numbers can be extremely overwhelming, extremely big. And you'd hate to take paper and write out, something with 46 different digits. That would take a long time. And so instead of doing that, we've developed a method called scientific notation. And what that does is, you see the little times 10 to the second right here. This is not the original number, 412.036. The 10 to the second tells us where the original number is, or what the original number is. It tells us what to do with the decimal point to get it back to the original number. And so if you see a positive number here, and like it is positive 2, that tells us that we're going to move it to the right. How many spaces? 2 spaces to get it back to the original number. And so if it was right here, we're going to move it 1, 2 to make it 412.03.6 to get it to the original number. What if it says 412.036 times 10 to the 4th? Well, to get it back to the original number, that means we have to move it to the right. Because it's positive, we have to move it to the right 4 times, which would make it 412.036. I know there's no 0 on the end here, but if we moved it 4 times, 1, 2, 3, oh, there's no numbers left. Well, we got to pretend there is and move around it, and we'll make that a 0. What if it's a negative number? Well, you do just the opposite. If we moved it to the right, if it's positive, to get back to the original number, we're going to move it to the left. If it's a negative number, to get back to the original. So we're going to move it 2 times to the left. And we have that number right here. Negative 4, move it 4 times to the left. Look, 1, 2, 3, uh-oh. We ran out of numbers. What do? We just pretend there's a number there and make that a 0 to get to this number. Okay, so there's another, something else that we need to understand about scientific notation. When we're moving to put into scientific notation, typically we want, we'll use that number up there maybe, or we'll just use this. Typically, if we have a number 0.003, 16, and we want to put that into scientific notation, we're going to move it 1, 2, 3 spaces right here. Now, why do we move it right here? Well, scientific notation, typically, their standard, their pro forma, is that we put it to the right, on the right side of the first non-zero number. But we have a 0 here, a 0 here, and a 3 here. The 3 is our first non-zero number. So we'll put it to the right of that. So that's going to be 3.16 times 10 to the negative 3. I know what you may be thinking. You may be thinking, wait a minute, we moved that decimal to the right. Shouldn't it be a positive 3? Well, now remember, it's wherever that decimal needs to go to get back to the original number. If it's a negative 3 here, we have to move it to the left to get it back to the original number. And that's why we have a negative 3 here. All right, so let's look at our 21.1. You can follow along in your book. Let me get there myself. But 21.1 gives us a division problem, multiplication and division problem. And so what we're going to do is we're going to make it or put it in scientific notation first. Well, I can see this is 0.0003 times 10 to the negative 6. I'm going to say 3 times 10 to the what? Well, let's first see how many spaces we had to move that point. 1, 2, 3, 4. Okay, so if it's 10 to the 6 already and we had to move it 4 spaces, what do you think that's going to be? What do you think? It's going to be 10 to the negative 10. Oh, I know some of you are thinking, oh, I thought 2 or negative 2. Well, remember, if we're moving it to the right, and it's original here, we're going to make it a negative more. So if it's negative 6 way back here for the original number, and we kept moving it right, 4 spaces, it was going to be negative 10 to get it back to the original number there. So we're going to multiply that by 4 times 10 to the what? So 1, 2, 3. 10 to the 3. To get it back to, now this is the scientific notation. To get it back to the original number, we have to move it 3 spaces to the right. Okay, we have 10 to the 0.006 times 10 to the 15. To get it to its scientific notation, we have to move it 3 spaces to the right. So this is going to be 6 times 10 to the 12. See, how did you get 12? Well, if it was 15, and I need to move it 15, positive 15, so that means positive 15 spaces that way. If I move it 3 spaces that way, then I've only got to move it 12 more spaces to get it back to the original number. And then I have 2, because it was 2,000, look, 1, 2, 3 spaces this way. So 2 times 10 to the 7th. Because if it was 4 spaces here to get back to the original number, I moved it 3 more spaces away from it, then that 4 plus the 3 spaces I moved away from it give us a 7. Okay, so here's what we do with scientific notation and multiplying. We're going to take 3 times 4, our bases. 3 times 4 is 12, times 10 to the, what do you think it's going to be? Well, remember, if we, way back in algebra, we learned that if we have a base, and 10 is going to be our base here, and we have, and those same base, 10 and 10, and those bases have powers, do we multiply the powers? No, we add the powers. So same base, 10 and 10, then we're just going to add those powers. So it's going to be a negative 7, because negative 10 plus 3. All right, so 6 times 2 is 12, times 10 to the 19th, because we just added the powers. Okay. Where does that take us from here? Well, pretty simple stuff. We just go ahead and work it as a division problem. 12 divided by 12 is 1. 1 times 10 to the, well, how do we rectify or justify this? Well, remember, we also said that we can take a number across a fraction bar. Do you remember what happens when we take a number across the fraction bar, whether we take it from the bottom to the top or from the top to the bottom? Yeah, it changes the sign of the power. So if we took this 10 to the positive 19 up here, it would become 10 to the negative 19. All right, so now at this point, it's still being multiplied technically. And so we have the same base, 10 and 10, and we have powers. So what we're going to do is just simply add those powers. Negative 7 plus negative 19 gives us a negative 26. And so our answer is 1 times 10 to the negative 26. Don't get discouraged if you look at scientific notation and you think still, oh man, I'm never going to get this. I struggled with it for years, but finally one time as a youngster it just clicked. And so it'll do the same for you. but it takes practice, it takes work, and you can get that. All right, let's look on to the next subject in 21.2. That's going to be two statements of equality. Okay, so number one tells us the ratio of two, by the way, before we get into this, we've done statements of equality before, and we've really started easy when we started to, well, we had systems of equations or linear equations where we had to find x or find y. And then we found the subscripted variables. Okay, those are all statements of equality. I'm going to do the same thing here, and we'll see how these relate. So the problem says the ratio of two numbers is 3 to 4. Ratio of two numbers. Now n and d, just for me, simply means numerator, denominator. A ratio, I'll put it in a fraction form, 3 to 4. And it also says that if we added those numbers, or it says their sum is 84. So n plus d is 84. What does that do for me? Well, if I have a ratio, recall that we can with any ratio that we're given, we can cross multiply if it's in a fraction form and get the same answer. So I can say n4 equals 3d. I don't like the way I did that. I'm not going to say n4. I'm going to say 4n equals 3d. And so we do have this now, which is in equation form, this which is in an equation form. So what do I do there? Let's make it simple. Okay, let's take this d here, over here, change sides, change signs. So now I have n equals 84 minus d. Look down here. Now I can say that 4 times 84 minus d equals 3d. Now that's going to be kind of a hefty problem, but that's okay. It's not a big deal. I think the book may have done it, may have solved for d instead of solving for, or may have solved for n instead of solving for d, but that's okay. These both work. So let's go and do our distributive property here. What is 4 times 84? Well, that's a hefty to handle. I like to say 4 times 80, well, it's 320. 4 times 4 is 16, so 4 times 84 is 336. So 336 minus 4d equals 3d. Okay, now I'm going to take this d over here, change sides, change signs. So now I have 7d equals 336. Now that's a pretty hefty number. How many times is 7 going to go into 336? Well, you can do the longhand. If your teacher allows you to use a calculator in Algebra 2, I guess you can do that. But I can say 7 goes into 33. 4 times with 5 left over. 5 and 6 is 56. 7 goes into that 8 times. So D is going to be 48. And if D is 48 here, it's just going to be 84 minus 48. And that's going to be what, 36? N is 36. And those trivial things that didn't show up here, the simple subtraction, it didn't show, but you can figure that out. Okay, so we understand when we're dealing with ratios, I like numerator, denominator, just cross multiply to get an equation, and then they already give us another equation that we can solve from there. All right, let's look at 21.3. About the same thing. It says that the sum of two numbers is 128 and their difference is 44. Now I have S and L and then L and S. Now what do I mean by that? Well, S is just small and L is large. And that's, again, it's just a denoting so I don't get them confused. So their sum, S plus L, equals 128. The difference, L minus S. I can't put S minus L because S would be the smaller one. That doesn't make sense if I'm subtracting that. So L minus S equals 44. Well, how do I work that? Well, let's make it as easy as we can. L minus S equals 44. Then I'm gonna go ahead and switch these and say L plus S equals 128. All right, that gives us a good elimination. We have opposite signs for the S's, the same number, the coefficient is 1. We can just cross those out and then add straight down. So 2L equals, well, we have 12 and a 7, and a 1. So I'm going to just add those up. So 2L equals 172. So what does that give us for L? Well, if we divide by 2 on both sides, L equals 86. And to find out what S is, if S plus 86 equals 128, we do our subtraction, and that gives us S is 42. All right, so there's our answer right there. So 2 statements of equalities. They're just giving them to us in a different manner, maybe than we're used to. Hopefully, we understood all this. If you didn't, you can leave a comment, or you can let me know. I'd be glad to help you out. But as always, keep working at it, keep plugging away. If you're having problems with it, and if you have the Saxon books, you know this already, that in the back of the books, the odd-numbered problems have their answers. Now, those aren't for you to cheat or just go back there and get an answer, because I'm sure, like my class, you're required to show your work. And so you need to let us know how you get there. But if you get stumped, sometimes it's nice to be able to see that answer, to see where you're going, and then sometimes that'll help you choose the right path to get there. So again, if you have any questions, let me know. I'll be glad to help you.